Okay, so let's continue our discussion from yesterday. Some of you asked me a few questions after yesterday's meeting, and I realized that I had goofed up a few things. One of the things I'd goofed up was many times when I wanted to refer to Raj Safra, I said Raj Pilka. Raj Pilka is a great paper to read. There are many such papers, but the one I wanted to refer to is Raj Safra, not Raj Pilka. The other thing is that I defined this polynomial g sub pi while talking about local testing. Let me repeat the definition, and then if this was one of the things that confused you, maybe it will help. So we look at a plane pi. G sub pi is defined as the bivariate polynomial of degree at most k that's closest to the restriction of f on the plane pi. On planes where the test passes, g sub pi will be equal to f restricted to pi. But on planes where the test doesn't pass, it's some polynomial of degree at most k that's closest to f restricted to pi. Okay. All right. So we'll continue our discussion about list decodable codes. So what we saw yesterday was a definition of what rho comma L list decodable codes are. Then we saw, at least over the binary alphabet, we saw some bounds on the best rate achievable by such codes. And the bounds were kind of close. So we'll continue on the same theme. And so the first theorem we are going to see is the result of Johnson, or a version of it. And this shows that codes, if the distance of a code is delta, then it already endows the code with some interesting list decoding properties. So if is a code with the relative distance delta, then C is rho comma L list decodable. For rho equals 1 minus square root of 1 minus delta, and L being order n. Okay, so it means so the distance of the code C is delta. It means if you look at balls of radius delta over 2 around any point, you are not going to see more than one code word. But this already tells you that even if you look at balls of radius 1 minus square root of 1 minus delta around any point, you're only going to see very few code words, some order n code words. There are various versions of this bound. So this is there are alphabet aware variants of this bound that give slightly better bounds. But this is the version we are going to prove. Okay, so let's just get a sense of parameters. Suppose we are working with Reed-Solomon codes. Okay, and the parameter k is like, let's say 0.01 times n. Okay, so delta in this case is, what's delta? It's 0.99. What is rho according to this bound? So rho is 1 minus square root of 0.01, which is 1 minus 0.1, which is 0.9. So it's a better bound than, did I mix things up? It's okay, right? Yeah. Okay. So it's not hard to argue that 1 minus square root of 1 minus delta is always greater than delta over 2. This is giving you, I mean, this bound is better. So in this case, delta over 2 would have been around 0.5. This is around 0.9. In fact, the next thing we will do after this is to show that for Reed-Solomon codes, we actually have efficient decoding algorithms that work with work in this regime of parameters. Great. So let's prove this. So there's many proofs known. The proof we are going to do is a simple combinatorial proof due to Kumar. So our goal is to consider the following problem. So let's say X is some vector in sigma to the n. And we are going to look at a ball of radius rho times n around X. And we want to count the number of code words in this ball. We want to say that the number of code words is at most order n. So it's one of these clean double counting arguments. So let's consider the following bipartite graph. On the left side, on the right side, the vertices will identify with coordinates 1, 2, 3 up to n. And on the left side, we will we'll identify this with all the code words C1, C2 up to CL that are in that lie in this ball. So the distance of X from any of the CIs is at most rho times n. Okay, and we will add an edge between a Cj and a coordinate I. So Cj is adjacent to I if Cj and X agree on I. Okay. Is the construction of the graph clear? And we would like to argue that the number of code words, so the number of vertices on the left hand side can't be too large. It's at most order n. These are code words in the ball of radius rho n around X. These are all the code words in the ball of radius rho n around X. Okay? All right. What can we say about, we can say some things about this graph based on its construction. So what can we say about the degree of every vertex on the left? So degree of any CI, the degree of a vertex is going to be the number of code words, number of coordinates on which it agrees with X. So this is going to be at least 1 minus rho times n. We can also say something more. We can say something about the size of the intersection of the neighborhoods of Ci and Cj. If we take two vertices here, we want to claim that they can't have too many common neighbors. Why? Yeah, because it's a code with distance delta. So this is going to be upper bounded by something like n times 1 minus delta, maybe minus 1. So this is a graph on which every vertex in the left has large degree, but no two vertices on the left can have too many common neighbors. And these requirements are sort of in tension with each other. That's what's going to give us a bound on L. Okay. So I said the proof is by double counting, but the question is double counting what? And yeah, and that's the clever part of it. So we will double count V's in this graph. Let me say what that means. We will count subgraphs that look like this. It's a V with a vertex here. So we'll count, count L, where Ci is adjacent to L and Cj is adjacent to L. Is that okay? Great. So let's count it. So let's count it from the left hand side. We can give an upper bound. How many V's can this graph have at most, given the properties that we already know? So it can have at most, so number of V's is upper bounded by something like L choose 2. So we pick pairs of code words and ask how many V's can they participate in. So what should it be? So L choose 2 times, they can have at most these many common neighbors. So it can't, so the number of V's is going to be upper bounded by n times 1 minus delta minus 1. Okay. Now let's do this count from the right hand side. From the right hand side, if the degree of a vertex, let's say L is dl, d sub L, how many V's can this vertex participate in? DL choose 2. So the number of V's, this is actually equal to sum over L in N, D sub L choose 2. So which means that if we compare these two things, we get sum over L, D sub L choose 2 is at most L choose 2 times N times 1 minus delta minus 1. Okay. These DLs are things that we don't really know, but we know something about DLs. What do we know about DLs? If we sum over DL, this is the number of edges in the graph, and we know something about the number of edges. So this is equal to, or this is at least L times 1 minus rho times N. Okay. Yes, so given these things, if we simplify things carefully, we are going to get our bound on L. So let me do one step of it, the one clever step, and then it's some calculations. So when you see this and you see this, what do you right, or convexity or whatever, right? So this function, the graph is convex. So what I'm going to do is use convexity and replace dl choose 2 divided by n. This is going to be at least sum over dl by n choose 2. Okay, so we take this thing, we plug it in here. So this implies, and sum over dl is something we know. Sum over dl is at least something. Right? So I can say L times 1 minus rho times n over n choose 2. That's what we can replace the left hand side by. This is at most L choose 2 times n times 1 minus delta minus. Okay, that's it. So at this point we simplify things, some things cancel out, whatever remains will tell us that L is at most n. It will actually give us L being at most n. Okay, are we good? That's the non-deterministic bit here. Yeah, but not really. I mean, so these two conditions. So intuitively, these two conditions tell you that something like this is worth looking at. This condition tells you that there are a lot of edges in this graph. This tells you that no two guys have too many edges and too many neighbors in common. But the right hand side is fixed. So if there were a lot of edges going out from here and you aren't getting too many common neighbors, then where are the edges going? So it's intuitive, but this formulation, once you have it, it's it's a 3-line calculation. Questions on this so far? We want a bound on L. We want an L that satisfies this bound. And that this will imply that L is order n. Okay, great. So Johnson's theorem tells us that any code with distance delta continues to be list decodable with list size at most order n, as long as rho is at most 1 minus square root of 1 minus delta. Right. So in particular, Reed-Solomon codes are going to be list decodable up to this radius with small list size. And then one can ask algorithmic questions about this. So we know that the list size remains small for Reed-Solomon codes even when we are looking at Hamming balls of radius rho, which is significantly larger than delta over 2. Can we design an efficient algorithm that given a received word finds code words in radius rho around the received word? And there are various versions of these questions and all of them are sort of interesting. One question to ask is, let's design an algorithm that will output everybody in the list around the received word within a radius of rho. The other question one can ask is, maybe you output something in the list. And they're all, they're all non-trivial questions to ask. So what we're going to see now is an algorithm for list decoding Reed-Solomon codes up to the Johnson bound. So let's write this. So the bound that Johnson gives. So rho that is given by it is 1 minus square root of 1 minus delta. And for Reed-Solomon codes, we know delta is 1 minus k over n. So this implies that rho is square root of k over n. So we want to decode Reed-Solomon codes, and rather it's easier to talk about rho n, which is square root of kn. So we want to decode Reed-Solomon codes with agreement being square root of k. Rho is rho is 1 minus square root. So rho n is n minus square root k. So we want to decode Reed-Solomon codes from error n minus square root of kn. So in the setting of parameters that we had there, so delta was 0.99. Right? So this is like 0.1 n, or this is like 0.9 n. Right? So we are trying to decode Reed-Solomon codes when 90% of the coordinates are incorrect, 10% of the coordinates are correct. When we were trying to decode Reed-Solomon codes from half the minimum distance, the number of correct coordinates was around 50%. So this is significantly better than, this is tolerating a lot more error than what the unique decoding algorithm was tolerating. The Johnson bound already tells us that the number of such code words is small. The question is, can we find them algorithmically? And so this was done in 2 papers. So let me mention the theorems. So Reed-Solomon codes can be efficiently decoded up to the Johnson bound. Sudan's theorem. So Sudan's result was decoding from n minus square root of 2kn errors. And Guruswami Sudan, a few years later, improved this to n minus square root of kn. So we are going to see all the details of this, and then I'll say a few things about Guruswami Sudan, but we won't have time to see the details. Is the setup good so far? Great. Remember, when we were talking about unique decoding Reed-Solomon codes, we said it's just a question of noisy polynomial interpolation. We are given a bunch of data points. We want to find a polynomial that passes through many of these points in 2 dimensions. So these are all algorithms that are algorithms for noisy polynomial interpolation, where they tolerate significantly more noise than what the Berkeley-Welch algorithm tolerated. Okay, so I would often switch to saying we are trying to decode Reed-Solomon codes from agreement square root 2kn and agreement square root kn, because the error is so large, it makes sense to focus on agreement. Okay, great. So this algorithm of Sudan that we are going to see, it's going to be a generalization of the algorithm of Berkeley-Welch that we saw in the class. So let's briefly recall what the algorithm for Berkeley-Welch was. What was the algorithm? There were 2 steps. The first step was interpolation. Okay, let's recall the setup. So the setup was that we are essentially given points alpha I, beta I going from 1 to n. Alpha i's are all distinct, and we wanted to find a polynomial of degree at most k that passes through a lot of these points alpha I, beta I. So the first step was interpolation. So what we did was we find a q of xy. This was of a very special form. It was of a naught x times y plus a1x non-zero, low degree, such that for every I, Q of alpha I, beta I is 0. And the second step was to output negative of A1 over A0. But let me write this slightly differently. So you output P of x such that Q of x comma P of x is 0. That's the same thing as outputting negative of A1 over. Right? This was the algorithm. What was it about this algorithm that forced it to require agreement n plus k over 2? Where did the threshold, where did the lower bound on agreements show up in the analysis of this algorithm? So the number of agreements needed, if you recall. So remember what? So we found ourselves a queue, we output this. But when we were proving the correctness of the algorithm, we said, well, let's take a P that is close to the received word and let's look at Q of x comma P of x. Q of x comma P of x is the polynomial of degree blah, and it has agreements more than its degree. And at every point of agreement, the univariate polynomial Q of x comma P of x is 0. So this is a univariate polynomial of degree n plus k over 2, but it vanishes at n plus k over 2 plus 1 points. So it must be identically 0. That was how the algorithm went. So the constraint on the number of agreements came from the degree of Q of x comma P of x, right? So the number of agreements needed to be at least the max over all P, degree k, the degree of Q of x comma P of x. Right? This is where the number of agreements came out of. So if we could have found ourselves a Q such that this degree is small, this quantity is smaller, we would have decoded from fewer agreements than what we needed in the unique decoding setup. So what forces us, so why not work with a Q of smaller degree? One way of working with a Q such that this quantity is small is to work with Q of smaller degree. The Y degree is fixed, so let's ask for A0 and A1 of lower degrees, which will tell us that this quantity will be smaller, so we'll be able to decode from more errors. What is it that forces us to pick A0 and A1 of large degree? The thing that forces us, so there were two things at play, two quantitative bounds at play. One was the number of agreements, which was lower bounded by this quantity. The other was how we implemented the interpolation step. The way we implemented the interpolation step was we said, well, these constraints are homogeneous linear constraints on the coefficients of A0 and A1. So let's get ourselves the linear system. But we needed a guarantee that the linear system has a non-zero solution. And the thing that guaranteed us that was that the system had more constraints than variables, had more variables than constraints. And hence the system must have non-zero solution. So we needed the number of variables in Q to be larger than the number of constraints we are imposing, which is n. How do you get Q to have more variables? Where we want A0 and A1 to have higher degree. So these are two requirements. We would like the number of agreements to be as small as possible, but we are forced to have the number of unknown coefficients in Q to be somewhat large so that the linear system has a non-zero solution. So these two requirements are in tension with each other. Right. There is an added issue here that we should have also thought about, which is that in the unique decoding setting, we know that the polynomial that's closest to the received word is going to be unique. And if you stare at this Q, just the structure of this Q will tell you that the number of polynomials P of x such that Q of x comma P of x is 0 is going to be at most 1. It can never be larger than 1 because any P that satisfies this must be equal to A0, A1 over A0. Okay, good. So now we would like to, so given all of this, we would like to modify this in a way that allows us to tolerate more errors, which means we would like to modify it in a way such that the number of agreements that we have to deal with here, this lower bound, is smaller. But we would also like to be able to have enough degrees of freedom in Q so that the linear system we set up has more variables than constraints. We also have to keep the fact that the solution is not going to be unique anymore because we are in the list decoding setting where maybe there are more than one polynomials in the ball that we are looking for. All right. Given all of this, what's a natural thing to try? So Sudhan's idea was that let's consider a Q of large y degree. So our Q now looks like A naught plus A1. So A naught, AIs are going to be polynomials in X times Y plus A2 of X times Y squared plus let's say AL or yeah, AL of X times Y to the L. So we are going to pick a Q of larger Y degree. This means there are more capital AIs to deal with. So they give us some more degrees of freedom. And eventually it will turn out that this will give us enough degrees of freedom that we can lower the number of agreements required for this to work from n plus k over 2 to square root of 2k. Is the plan clear? Okay, great. So we are going to consider a Q of this form. Now we have to ask, well, what degree constraints do we want on AIs? Remember, when we were doing this here, we carefully choose the degree of A naught to be n minus k over 2, A1 to be n plus k over 2. So what degree constraint should we pick here? This should really be dictated by what is happening here. So eventually we are going to, we are going to look at Q of x comma P of x for an arbitrary degree k polynomial P, and we are going to have to bound the degree of this quantity. So this is A naught plus A1 times P plus A2 times P squared, so on, plus AL times P to the N. So what's the degree of this? What is the degree of this bounded by? If P is of degree at most k, so degree of Q of x comma P of x, it's at most what? It's at most max over I, degree of AI plus I times k, right? That's what it is. So this is the quantity that we want to minimize while trying to maximize the number of degrees of freedom that AIs give us, because we have to set up a linear system. So if you stare at this, we will pick a parameter d that we are going to set later, but d is going to be roughly square root 2kn. And we will set the degree of AI to be d minus I times k. Okay? Is that okay? If AI is set to be d minus I times k, then all of these terms are going to be degree capital D. So this quantity is going to be of degree capital D. Okay? Good. Great. So given this in mind, let me write the algorithm and then we'll analyze it. So we find ourselves a Q with, let's say, I going from 0 to L. L is also a parameter we'll pick later. So we want a Q of xy with y degree L, such that the degree of each AI is at most d minus k times I. And for every j, Q of alpha j comma beta j is 0. This is the first step. This is the adapted interpolation step. What changed was that the y degree of Q is no longer 1, it's something larger. And the second step is to output all degree k polynomials P of x such that Q of x comma P of x is identically 0. Okay. So we'll talk a little bit more about how these steps have to be implemented, but Is the sketch of the algorithm clear? It's exactly the same algorithm as Berkeley-Welch, with where we are looking at a Q of more general form with higher Y degree, and we are going to, instead of there being a unique polynomial P of X such that Q of X comma P of X is 0, we'll output all P of X with these properties. Are we good so far? Questions? Good. One question. How do we do step 2? Step 2 was trivial in the previous case because the Y degree of Q was 1. So the only way Q of X comma P of X was going to be identically 0 was that P of X was equal to minus of A1 over A0. That was the only way this could happen. But here we are looking at a bivariate polynomial Q of xy of potentially larger Y degree, and we are asking for all polynomials P of X of degree at most k such that Q of X comma P of X is identically 0. So step 2 needs some discussion. So okay. So here's so what do we need? So we want P of X such that Q of X comma P of X is identically 0. This, I claim, is the same as, happens if and only if y minus P of X, the bivariate polynomial y minus P of X divides the bivariate polynomial Q of X. Why is this true? Does this look familiar? Right? This is a remainder theorem or factor theorem from school, except there we would typically talk about univariate polynomials, and here we are working with bivariate polynomials. But the way to think about this is that you should think of Q of xy as a univariate in the variable y. And then this is with coefficients coming from some field that contains the variable x in it. And then this is exactly the remainder theorem or the factor theorem from school. So any polynomial P of X that has to satisfy Q of X comma P of X being identically 0 must actually come from factors of Q of xy of the form y minus P of X. And there's a more general theorem that so there are efficient randomized algorithms for factoring bivariate polynomials over finite fields. Okay, so how do we do step 2? Well, we take one of these algorithms off the shelf, apply it with input Q of xy, figure out all the factors of Q of xy, all the irreducible factors of Q of xy, pick out the factors that look like y minus P of X for a polynomial P of degree at most k, and output all such P's. Are we good? I'm not going to talk about this algorithm at all. We are going to use this as a black box. The factoring algorithm is not deterministic. Yeah. Why? Okay, I can say something. So the bivariate factoring algorithms use the univariate factoring algorithms in them. And the univariate factoring algorithms are not deterministic. In fact, we don't know how to compute square roots. We don't know how to factor degree 2 polynomials over finite fields deterministically. Yeah. Right. Yeah. So if we are in the setting when Q is poly n, then we can actually just use deterministic algorithm that have running time polynomial in the field size, and they will do this. In coding theoretic context, maybe that's a standard setting to work in. Yeah, but more generally, this algorithm is randomized. Questions? Q may have other factors. We will factor Q and we will only get our hands on factors. These are the factors that are interesting to us. Other factors we can discard. Nothing guarantees that Q will only have factors of this kind. So if Q has no such P's, this means there was no polynomial that was close to the received word. So we will argue that if there exists a polynomial of degree k such that P has large agreement with the given data, then there will exist a P, then that P will actually be a factor of this kind of Q. So if Q has no factors that look like this, then this means that there was nothing, the received word given to us had nothing in its, in a row n ball around it that was a code word. Other questions? Great. So so now let's convince ourselves that all of this will work. So what do we need to do? We need to check. Oh, by the way, given these things, we know that we can implement all of this in polynomial time, maybe with randomness based on the setting. Right. The first step is exactly the first step in the previous case, where we will set up a homogeneous linear system of polynomial size, and then use our linear system solver to find a solution. We will take that Q, find a non-zero solution, take that Q, invoke our factoring algorithm on that Q. It gives us some factors of this kind. We will work with those. So everything can be done in polynomial time, maybe with randomness. Okay. So what we need to argue is, so remember the Berkeley-Camp-Wells setup. We have to argue that there is a non-zero solution. There is a non-zero Q that one can find. So the linear system we are going to form has a non-zero solution. And if P is a polynomial that is close to the received word, then Q of x comma P of x is 0. These are the two things remaining to argue. So claim 1. So for D greater than square root of 2 nk, maybe even greater than or equal to, the linear system in step 1 has a non-zero solution. And claim 2 is that if P for join X, degree at most K, such that the agreement of P with the received word, so alpha I, beta I going from 1 to n, this is greater than square root 2 nk, then Q of x comma P of x is identically 0. Given these two claims, this will complete the analysis of the algorithm. Both of these are these are for a suitable choice of L. We will pick, L was the Y degree, right? So we will pick L to be as large as we can, given these constraints. Given the bound on D, L can be at most D over K. So L can be at most 2n over K, because the AIs need to have non-negative degrees. So the parameter L for this choice of D, L is going to be set to D over K, which is square root of okay. Right. We agree that given these two claims, this will complete the analysis. So let's prove the two claims. How should we prove claim 1? We have seen these things in Berkeley-Camp-Wells. Yeah. L was the Y degree of Q. We take it as large as possible with the constraint that the degree of Q of x comma P of x should be at most capital D. How should we do step 1? How should we prove claim 1? Claim 1, step 1 here is a linear system. We will again look at the linear system, look at the number of constraints, number of variables. If the number of variables is one more than the number of constraints, we are good. So proof of 1. So how many constraints do we have in the linear system? N. The constraints are again nothing changed. For every j, we want Q of alpha j, beta j to be 0. How many variables does this have? How many variables? So the variables come from the coefficients of AIs. The number of variables contributed by an AI is like one more than the degree of AI. So this is sum over I, degree of AI plus 1, which is what is degree of AI? So this is sum over AI degree of AI is d minus ki plus 1. What is this? So how do we do this? Summation goes from I equals 1 to, I equals 0 to roughly d by k. If you do this summation, I'll tell you what you get. You get something like, you get something greater than d square over 2k. Okay? You can do the summation. So whatever this quantity is, the number of variables is greater than d square over 2k. So if d square over 2k happens to be greater than n, then we are good. But if you pick d to be square root 2nk, then d square over 2k is going to be greater than equal to n. So we are good. So step 1 will give us we will find a non-zero q. That is the solution of the linear system we are getting in step 1. So let's argue the second claim. So proof of claim 2. So in the second claim, we have to show that if P is a polynomial that has large agreement with the given data, larger than square root 2nk, then Q of x comma P of x is 0. And the argument is going to be very similar to what happened for Berkeley-Campbell. So let R of x be defined as Q of x comma P of x. So this is a univariate polynomial. What is the degree of this polynomial? What's the bound on the degree? The parameter capital D was chosen in a way that the degree of this doesn't exceed capital D. So degree of R is less than equal to capital D. And again, observe that if P of alpha j equals beta j, then R of alpha j, which is equal to Q of alpha j comma P of alpha j, which is Q of alpha j comma beta j, this is 0. This was an interpolation constraint that we had imposed. So at every point of agreement, at every j such that P of alpha j equals beta j, we are getting a root of R of x. So this implies that if the agreement between P and the received word is greater than D, then R has greater than D roots. Greater than D roots, which implies that R must be identically 0. The same argument that happened last time, it's exactly the same argument as Berkeley. Great. So that completes the analysis of Suthen's algorithm. Questions so far? No? Okay, great. Good. So, but we have only been able to decode from agreement square root 2kn. In order to get to agreement square root kn, we need a few more ideas. And the one main new idea is the notion of multiplicities. Okay, so let me define it and then say how it's used. So we'll say that a polynomial, Q, okay, so Q vanishes with multiplicity at least S at a point alpha if all the partial derivatives of Q of order less than S vanish at alpha. Okay, maybe let's start by thinking of Q as a univariate polynomial. If Q is a univariate polynomial, we say that an input alpha is a zero of multiplicity at least s or a root of multiplicity at least s of Q if all the derivatives of Q of order less than s vanish at alpha. Right, I'm saying derivatives. Yeah, we should ask what derivatives. We are over finite fields. So for the rest of this discussion, let's assume that we are working over a field of characteristic somewhat large. And yeah, derivatives are going to be syntactic standard derivatives. So the first derivative of x to the n is n times x to the n minus 1. The second derivative is iteratively defined. And then we linearly extend it to all polynomials. So these things no longer have any analytic meaning, but it's a syntactic linear operator on the ring of polynomials. Okay, so so far we have been working with polynomials vanishing at points. Now we want to introduce the notion of polynomial vanishing with high multiplicity at a point. What's the advantage of working with polynomials that vanish with high multiplicities? So here's a fact. So we know that a univariate polynomial of degree d at most has a non-zero univariate polynomial of degree d has at most d zeros, but something stronger is true. So a univariate, or rather, let me write it this way. So let's say p of x and f of x, f of giant x is a non-zero univariate, then so then let's sum over all alpha in f and look at the multiplicity of p at alpha. This is going to be at most the degree of. So far we have been counting zeros, which is really counting points with multiplicity at least 1. But something stronger is true. If you have an input alpha where p vanishes and its derivative vanishes, meaning p has multiplicity at least 2, then the weight of that point in the zero counting business should be 2, not 1. So this says let's run over all alpha in f. We will look at the multiplicity of p at this point alpha. That's the weight of this point. And the sum of those things is at most degree of p. So far we have been working with just checking whether the multiplicity is at least 1 or not and counting that point as 1. Great. And the definition can be extended to working with bivariate polynomials, multivariate polynomials in general. So we'll say that a multivariate polynomial has a zero of multiplicity s at a point alpha if q and all its partial derivatives of order at most s minus 1 vanish at alpha. Okay, again, these derivatives are all syntactically defined. If you want to extend this to arbitrary finite fields, you have to work with an appropriate notion of derivatives. But we will just confine ourselves to finite fields with sufficiently large characteristics so that all of these things make sense. Questions so far in the definition? Okay, so similar to this statement, there is a high multiplicity variant of the Schwartz-Zippel lemma. The Schwartz-Zippel lemma was also counting the number of zeros of a non-zero polynomial on a grid. You can actually count zeros with multiplicities and get the same bound that the Schwartz-Zippel lemma gets. All right. So given this definition, now we are in the situation to talk about Guruswami-Suden. So the main idea of Guruswami-Suden was that in the current algorithm, we are trying to find a polynomial q that vanishes at alpha j beta j for every j. And then while arguing about the algorithm, we argue that at every point of agreement, q of x comma p of x has a root. And then we do these counts and get a bound. Guruswami-Suden said, well, instead of asking for a q to vanish at alpha j beta j, let's find ourselves a q that vanishes at alpha j beta j with high multiplicity. So find a non-zero low degree q such that the multiplicity of Q at alpha j beta j is large. It says at least M. And the second step remains exactly the same. So output all Q of all P of X degree K such that Q of X comma P of X is identically 0. So that's all that changed. But this change in itself should be counterintuitive. We want to tolerate more errors. So we want to decode from smaller number of agreements. So really what we should be looking to do is to try and get our hands on a Q of smaller degree. If the degree of Q of X comma P of X was not square root 2 nk as in this analysis, but it was square root nk, then we would be done. We would be decoding up to the Johnson bound. Guruswami Sudan say, well, what they are going to do is to impose even more constraints on Q. So instead of just asking for a Q that vanished at alpha j beta j, now we are going to ask for all the partial derivatives of order at most M of Q to vanish at alpha j beta j, which means for every j, this is no longer a single constraint. It's a large number of constraints. How many constraints? It's M plus 2 choose 2 constraints, right? Or something like that. It's the number of partial derivatives of it's the number of monomials of degree at most M minus 1 in 2 variables. So M plus 1 choose. So instead of asking for a single constraint at every j, we are now asking for more constraints. So we are imposing more constraints on Q, which sort of should force us to pick Q of larger degree. So where is the gain coming from? So the gain comes from the fact that they can argue, because they have interpolated a Q with stronger structure, they will be able to argue more about Q of X comma P of X at every point of agreement. And their main claim is that if, is this visible on this side? I'll write a line and then leave it. So if P of alpha j equals beta j, then Q of X comma P of X vanishes with multiplicity at least M at alpha j. So in the analysis so far, we have argued that if P of alpha j equals beta j, then Q of X comma P of X has a 0 at alpha j. Guruswami Sudan argue more. They show that because of the way we had interpolated Q, at every point of agreement, you have a 0 of multiplicity M. So yeah, so this is the kind of count that we are going to do. And at least I don't see, given this sketch, I don't see a way of seeing that this algorithm will give us better bounds unless I work out the details. I do the calculations. So we are imposing far more constraints on Q that forces us to pick Q of large degree, but we are getting more out of every point of agreement. And then somehow at the end of it, this yields an algorithm where the agreement only has to be at least square root nk and not square root 2 nk. So that's a good exercise to go and do. So you know exactly what the algorithm is. Maybe go back and analyze it. Questions? If you tune the parameters appropriately, yes. The way I have stated it, yeah, I haven't chosen M, right? So there's some choice of parameters. But you can choose parameters in a way that will ensure that P is a root of somewhat large multiplicity. And that gets better bounds on the list size than what this algorithm will give. Other questions? Okay. Let me point out something interesting that happened already in Sudan's algorithm. So we went on this adventure of trying to decode Reed-Solomon codes efficiently after seeing the Johnson bound, which told us that the number of polynomials that are close to a received word, close to any vector within with agreement at least 1 minus rho times n is small. So Johnson bound gave us a guarantee that the number of polynomials we are looking for is small. Right? But note that Sudan's algorithm did not need that guarantee. We didn't really go and use Johnson bound somewhere inside the proof of Sudan. In fact, the analysis of the algorithm also gives you a bound on the list size. It tells you that the list size is small. So Yeah, so somehow, I mean, this algorithm is, it exists independent of Johnson. It doesn't really use Johnson inside. Something weird. Great. The list size didn't come into play, but you can get a bound on the list size from here. So we are going to output all polynomials p of x such that q of x comma p of x is 0, which is the same as saying that p of x is a y root of q. But the y degree of q was at most d over k, square root 2n over k. The number of y roots can't be larger than that. So this gives a bound on the list size. Yeah. But we didn't use, this algorithm doesn't use any guarantees. It doesn't need an independent guarantee on top. In fact, the bound you get here is slightly better than the bound we were getting in, here you get a constant. Other questions? What became? Oh, so a multiplicity m constraint on a bivariate is saying all partial derivatives of order at most m minus 1 should vanish. So that's it. You had a question?
Yeah, for even lower.
Right, good. That's a good question. So one question to ask is what happens to Reed-Solomon codes beyond the Johnson radius? The Johnson bound was just it was just one upper bound on a non-trivial parameter rho that guaranteed that the number of code words in the ball is going to be small. So we don't really understand Reed-Solomon codes well beyond the Johnson bound. So when we defined Reed-Solomon codes, we said, well, let alpha 1 up to alpha n be all the points in the field. Right? But we didn't use the fact that these are all field elements anywhere. All we used was that alpha i's were distinct. So you could work with any set of evaluation points in your favorite underlying field that you're working in. And so far, all these algorithms work independent of what the choice of alphas is. When we go beyond the Johnson bound, things become murkier and messier. So we know that the number of code words in a Hamming ball of radius larger than the Johnson bound continues to be small if alphas are chosen randomly from a somewhat large field. But we know that the list size does grow for certain choice of alphas. So we don't understand things much. Certainly no algorithms are known to decode Reed-Solomon codes. Suppose that we got our hands on an alpha which gives us Reed-Solomon codes such that the number of code words in a Hamming ball of radius larger than larger than what's given by Johnson continues to be small. Suppose we have this promise with us. Can we design an algorithm that will list decode from these parameters? We don't know. We also don't know explicit construction of Reed-Solomon codes that are combinatorially list decodable beyond the Johnson bound. We know random things work, but that's about it. Other questions? Yeah. Right, it gave it for every code, yeah. But you get root 2n by k when this is not the Johnson, right? Root nk would have been Johnson. We are further away from Johnson. So here you get a constant. For root nk, I think you don't get a constant. But if you are like 1 plus epsilon times root nk, then you get a constant. M, you can pick it to be larger than, I don't know, square root nk, or maybe nk, certainly it should work. It's humongous. It's polynomial in the whatever block length and dimension. Yeah, if you want to get square root nk. Right, but the degrees will become larger. The degrees become large. Other questions? Okay. How much time do I have? 2 minutes? 5 minutes? 5 minutes. Okay, so let me say some more things. So this was the state of art for these codes around 2000. But since then, we have been able to construct variants of Reed-Solomon codes that are now known to be list decodable far beyond what Johnson bound gives us. So one of these codes is multiplicity codes. So that those are based on some of the things we were talking about there. So the code words here correspond to evaluation of a univariate polynomial of low degree and evaluation of all its derivatives up to a high order at every point. So we pick points alpha 1 up to alpha n again. At every alpha I give you f of alpha, I give you p of alpha I, p prime of alpha I, p double prime of alpha I, etc. So it's like a packet. So the alphabet size is now q to the s, if q is the underlying field. For sufficiently large S, these codes are known to be list decodable basically up to the parameters that are essentially the best that we can hope in this case, and the list size remains constant. And there are people around here and this week and next week who have proved better and better bounds on the list size. So now we know really good bounds on the list size for multiplicity codes. These weren't the first variant of Reed-Solomon codes that with this kind of a property. The early variants were Parvaresh-Waddi codes and then folded Reed-Solomon codes. And folded Reed-Solomon codes are as good as univariate multiplicity codes with respect to their list decoding properties. Parvaresh-Waddi codes, they are also variants of Reed-Solomon codes. They go beyond the Johnson bound. They were sort of the first such construction that went beyond the Johnson bound. And folded Reed-Solomon codes, univariate multiplicity codes, for sufficiently appropriate tuning of parameters are known to approach what is called the list decoding capacity. So they have the best parameters we can hope for. Okay, I'll just stop there. But maybe I'll just write the keywords. So the things to look for are folded Reed-Solomon codes. And okay, so I'll stop here. Other questions?